So let's continue about the factor that influence bioavailability. After we have covered the physical-chemical properties on their influence in dissolution and bioavailability, let's go into the formulation factor. It is related to the excipient and also the compaction force during manufacturing process. Alright. Okay. The drug usually seldom administered alone, and rather they are given as part of formulation in a combination with one or more agent that's called excipient. Okay, and the selective use of these pharmaceutical excipient produce dosage form of various type. Okay, if you need to have the tablets that they can bound together, perhaps you need to add binder. And if you no need to bind the particle together, you can put your tablets into capsule and so on and so forth. Okay, the pharmaceutical ingredients usually solubilize, suspend, thicken, dilute, or emulsify, or they stabilize, they preserve, or they are adding as color, they are adding as flavor, or a fashion medicinal means just to put in to make your dosage form fancy, okay, into efficacious and appealing dosage form. Okay, so once again we go into the example of diclofenac sodium. When you have two different manufacturers, okay, even though they undergo the same manufacturing process, but still they can't produce a profile that's different in these solutions, and eventually you will have different in the bioavailability. And in this case, this might actually caused by the formulation factor. Okay, so once again we recap the process of a tablets when they are ingested in the ingested orally. So when a tablet go into your oral, and they need to go through this integration to generate granule aggregates, then they need to deaggregate to become fine particles. Okay, after they become fine particles, they need to dissolve, all right, and into the drug solutions. And here, to support this integration process, you need this integrant, this integrant agent, all right. And if you want to prevent deaggregation, then you might need to add in some something like a disintegrant as well. And following oral administration of the tablet, this integration must first occur. The speed and efficacy of this process will determine how much the drug is actually available for subsequent step. So here is the main step. So in formulation factors that affect bioavailability, it is related to the excipient used in the formulations. Okay, and we can understand that by looking at the composition of the excipient in the formulations. And usually excipient are inert substances that are added to the formulation to provide certain functional property. For example, improve the compressibility of the powder. Okay, so in factor affecting this solution, formulation variable is divided into excipient and compaction force, and in each excipient, okay, each of the excipient can affect the final performance of the drugs. Okay, these include the diluent, the binder that we use, the disintegrant that we use, whether we add in any surfactants to increase the dissolution, okay, and the lubricant that we use for the tableting process, the glidant for powder flow, and the sorbent for absorb some liquid. So all these can affect the bioavailability of the end product. So let us look into the diluent or filler to dilute the drugs in order to produce tablets. So usually when we have a dosage, the dose of a drug that is very small and is not sufficient to produce into tablets, so we may need diluent to dilute the drug in order to produce the tablets or in a reasonable size. Okay, so the smallest tablet diameter will be 3 millimeter, and the smallest capsule size is 5. Okay, and what we can use as a diluent, usually lactose, microcrystalline cellulose, dicalcium phosphate, sucrose, mannitol, or starch. Alright. However, when you add in all this, it can affect the dissolution if the excipients are hydrophobic, and they can affect the wettability and water penetration into the tablets. Because if they are hydrophobic, they are not easily wet, okay, and they would not draw the water into the tablet, so you will have very low water penetration. All right. So the influence of different filler on drug release from HPMC, slow release tablet. All right. So if you look at theophylline, and we have MCC, lactose, and starch. Okay, T15 is the time for 50% of drug being released. Okay, and if we look into here, starch, they use up the longest time to release only 50% of the drug. So the hydrophobicity of starch is much more than lactose. So they are more hydrophobic. That's why they will cause a delay in the drug release. Same thing happened to the chlorpheniramine, that the starch, they have the highest 50%, the longest time for 50% of drug being released. Okay, and the second excipient is binder. What is the function of binder? Is to ensure that the granule and tablets can be formed with the required mechanical strength. Alright, and a dry binder is a dry powder mixed with other ingredient before compaction. For example, dry binder, you can use microcrystalline cellulose, you can use PVP, you can use any cellulose derivative, which is HPMC, it is hydroxyl, propyl, methyl cellulose. Alright. Okay, a solution binder is a solution used as a granulation liquid during the wet granulations. So example, starch, gelatin, or any cellulose binder. Okay, and you will gone through the wet granulation experiment with Prof. Habibah. Okay, if your binder liquid is too viscous, okay, for example, when you use a HPMC, okay, they can form a very viscous layer and affect the disintegration and dissolution process. Okay, hence the amount and type of binder used is very important. Okay, so the viscosity of PVP is more than the acacia, more than HPMC, and more than gelatin. This table shows the effects of various granulating agents on dissolution of sulfadimide tablets. Okay, the T50 is the time taken for 50% of drug release. Okay, in this case, if you can see, starch paste takes the longest time, followed by gelatin, followed by MCC. This means that the granulating agent in starch paste is stronger, means they use a stronger binder that they can bind the tablets strong, so that they will take a longer time for the drug release. Okay, so the third ingredient is disintegrant. Disintegrant added intragranularly or extragranularly To ensure that the granule and tablets will break into a small fragment to release the drug for a rapid dissolution. The mechanism of the disintegrant is to promote water uptake first, and they rupture the tablet. Okay, so conventional disintegrant use up to 10% weight per weight. Example of conventional disintegrant is starch, or you can use also high swelling disintegrant, which is being used in around 1 to 5%. Example is a cloth-linked PVP, modified starch, sodium starch glycolate, and pre-gelatinized starch. Okay, insufficient disintegrant can affect disintegration and dissolution. For example, tobutamide tablets, the bioavailability of tobutamide reduced when the disintegrants was half. Since this integration process is the first process that experienced by a tablet when the tablet is consumed orally, so it must be noted that the type and amount of disintegrating agents can significantly control the overall rate of dissolution and eventually the bioavailability of a drug dosage form. Surfactants can also be added to a tablet formulations. So addition of surfactant in a formulation can reduce surface tension and contact angle of the solid to its dissolution medium, and this will increase wetting of the tablets. When wetting of the tablets being increased, this will promote the water penetration of the medium into the solid, and the water penetration go in via capillary force, which in turn will influence by porosity, surface tension, and contact angle. Okay, and when the water penetrate into the solid, okay, and they were in contact with the disintegrant, and here after that the disintegrant will swell, then cause the rupturing of tablets, okay, into granule. Okay, so the addition of surfactants actually assist in disintegration process. This is just a schematic diagram of tablets that wet by a drop of dissolution medium. So during the manufacturing process of tableting, lubricant also added to ensure the tablet form are ejected with low friction between the solid and the die wall of the tableting machine. Okay, and usually lubricant is added in a low percentage, which is less than 1% weight over weight. Okay, and it's also used to reduce powder to metal adhesion in powder filling of hard gelatin capsule. Okay, so in tableting, it reduces the friction between the solid and die wall, and in the capsule manufacturing, it reduces powder to metal adhesion, so it reduces the adhesions. Okay, so example of lubricant that you can use, and usually in tableting we use a magnesium stearate, which is the most common one, or you can use stearic acid, surface active agent, high molecular weight polyethylene glycol, for example PAX 6000 or PAC 8000. Okay, however, there are problem with lubricant because they will promote capping during the compression and also retardation of dissolution if overused. So you don't add the lubricant more than 1%. Okay, because for example magnesium stearate is very hydrophobic. Okay, and if you overuse them, they will reduce the dissolution. All right, and capping is when you have your tablet like this. Okay, when you punch them, okay, you will get some powder stick on top of the punch, okay, and this is what you call capping. Okay, so for example, magnesium stearate are hydrophobics, so too much you will reduce the wettability of the tablet and water penetration into the tablet, hence you will affect the disintegration and as well as dissolution, as I have mentioned just now. Okay, this is the graph for the effects of lubricant, okay, dissolution curve of magnesium stearate. All right, so the dissolution of salicylic acid, okay, when you have 3% of magnesium stearate or you have no magnesium stearate, okay, in the graph A, I think it's this one. When you have no magnesium stearate, okay, the release of salicylic acid is fast, okay, but when you have magnesium stearate, the hydrophobicity, all right, of magnesium stearate, has slowed down the dissolution profile. All right, so the same thing happened to the graph B, okay, when you have no when you have no magnesium stearate. All right, here is no magnesium stearate, and when you have 3% of magnesium stearate, here this is 3% of magnesium stearate, and this is no magnesium stearate, and this is with surfactant. Of course, as I said, with surfactant you will increase the wetting, okay, and you will enhance the water penetrations and then the disintegration process. And if you compare no magnesium stearate and 3% of magnesium stearate, and then you can see the effect of magnesium stearate due to the hydrophobicity of this substance. And this is one of the example of effect of lubricant, magnesium stearate, okay, on a plasma concentration of drug sample. Let's say we call it sample A. When you have the higher percentage of lubricant, you will see the absorption is slower in rate, okay, due to the delay or slower in disintegration process. All right, and when you have a lower percentage of magnesium stearate, of course, then you will expect to have the higher plasma concentration. Okay, so Glidant also add into the tableting process to improve the flowability of the powder. Okay, so what type of Glidant that usually they use is talc, around 1 to 2%, or they add in a colloidal silicon dioxide, 0.2%. all right, and sometimes sorbent also added into the formulation to absorb some quantity of fluid in an apparently dry state. So what kind of sorbent that they can use? Example, microcrystalline cellulose, MCC, colloidal silicon dioxide. Okay, both of the above can affect wettability and porosity of tablet if used in excess, so hence affect the disintegration and dissolution. So the percentage of this thing, for example, of these products in the formulation should be carefully determined. So the manufacturing variable can also affect disintegration and dissolution. For example, compaction force. If you have too high compaction force, they can cause the reduce in the porosity, okay, of the tablets, and they will store excess mechanical strength in the tablets, and the tablets will not disintegrate. And this can also be affected when they have a different size or a wide size range. Okay, so for example, when you have the particles size that is too fine, okay, they can reduce the porosity. Okay, so before compression, they already reduce the porosity. After compression, you will further reduce the porosity, and hence the water penetrations to the tablets is being reduced. Okay, when you have a big size range, when you have a wide range, and you have a particle big one like this, okay, before compression, and you have the small particles that fill in the gap between the big particle, and this can also reduce porosity of the tablet. Okay, and when you go through the compaction process and the porosity being further reduced, okay, this will eventually cause the reduce in water penetration and subsequently reduce in disintegration. Alright, this graph shows the porosity changes when you use a different pressure for apply to the tablet. Alright, so when you increase the pressure, of course the porosity will be reduced. Okay, and this table shows the influence of compression force on drug release at 50%. So this is time used for 50% of drug release. When you have the higher compression force, that you have the porosity that is been reduced. So theoretically, it will take a longer time to wet the tablet due to the lack of porosity in the tablet. So you will have the longer T50%. The same happened to chlorpheniramine.